This is a tutorial following the paper Code-Free Development and Deployment of Deep Segmentation Models for Digital Pathology. Here we present a code-free pipeline for deep segmentation of digital pathology whole slide images using only open source software. All software used in this study can be freely downloaded online. The first step of the pipeline is downloading and installing QPath 0.3.0 and the latest version of Microscopy image browser standalone version. First we'll present manual annotation in QPath. So after opening QPath, one would create a project directory and add the VSI images. QPath is very suited for annotating whole slide images with fast rendering and many options for annotating. So after a quite extensive first round of annotating perhaps 10% of the slides, here we present the 5 out of 10 slides annotated. One would use the export script made available on GitHub, no code seg. You simply copy the export script into the script editor and change the values for downsampling, glass threshold per patch, and the percentage tissue per patch which you want to export. This is to avoid the large amount of glass background patches. So you run the script in batch for all the annotated slides. The slides are then exported into a tiles folder. The images are exported into an images folder and labels into a labels folder, which can be directly processed by DeepMIB. So you create a folder for DeepMIB, copy the images and labels you have exported from QPath into the DeepMIB folder, and now you're ready to start training a deep segmentation network in DeepMIB. You create a training, test and results folder and put the images and labels into the train set folder and take out however much you want to leave for the test set. Here we leave 1 VSI out of 5 for the test set and simply move them into corresponding images and labels folder in the test set folder. So now it's time to open Microscopy image browser, and under tools you'll find the deep learning segmentation. You have to specify the previously made training and test set folders and also a empty results folder. We'll put 3% of the images for a validation set, activate parallel processing for a much faster processing of the images, set the correct file name or file extensions to TIFF and PNG. Models are PNG and images are TIFF from the export from QPath. So after pre-processing is done, you set the settings for training. Here it's set to 512 by 512, which is quite memory intensive, so 256 by 256 or 128 by 128 is a good alternative. Depth 6 is chosen. We have two classes, mini batch size of 16, which can be decreased to decrease the use of memory. Number of filters is set to 32, which is also quite high and can be decreased to decrease the use of GPU memory. We have used the rescale 01 normalization for input, and you also have extensive options for augmenting the data during training to decrease overfitting. You also have extensive options to tune hyperparameters. So you are now ready to start training, and click the train button. Here we demonstrate the training on 4 BSIs for 250 epochs. So after running the first training, you do a prediction of the test set, which is the first VSI, which we put in the test set folder. And here we see a very good segmentation result after a short amount of training. You can export the results for the test set into an Excel file and get individual patch level scores for all the patches. If you later want to run predictions on the entire train set and select out the hardest patches, so-called hard mining, for example. Now we'll go through the export of patches from the unannotated slides and prediction by the network in DeepMIB. Here we will set the percentage threshold of tissue down to 1%, not to miss any tissue. We will batch process this with the export script and just remove the labels, which are empty in this case, since there are no annotations. We will specify the folder which we exported from QPath and just choose pre-processing is not required, so we predict directly on the exported TIFFs. We make another results folder for this prediction and specify that as a results folder. We then use the trained network to predict the next 5 slides, which we have exported from QPath, and this generates .model files, which then can be loaded in MIB. And these model files can be visualized on the patch level before saving it as TIFF files again, for example in the result scores folder. And this makes it now possible to import back into QPath for improvement of the predictions and visualization on the whole slide image level. So we copy the import script from the docode seg repository on GitHub. We specify the folder to which we exported the TIFFs and changed the slashes, and here we just imported for one slide, that is the first unannotated slide. You can see the predictions of the network and seems to work well, so we will just import it to all the rest of the slides and check that the import was successful. And now it's possible to use QPath's speed and tools to improve the annotations. For example, remove small fragments and holes, etc. So improving predictions is quite time consuming, but is here demonstrated how this can be achieved in QPath. So here we remove fragments smaller than 150 square micrometers and holes smaller than 100 micrometers. We add some mist epithelium, remove some wrong false positive annotations predicted by the network, and we can also create a workflow script and remove fragments similarly for all the predicted VSIs using batch processing and the script editor. So after some more final improvements and corrections of the predictions imported from DeepMIB, we now have a twice as big data set, which can be further expanded to several more VSIs, depending on how large the data set is. So improvement of the annotations on the VSI level versus the patch level in Microscopy image browser gives a whole other overview and is better for annotation in our experience. So we can now export a new data set of 10 annotated VSIs. We started with 5, which was much faster to create, since we could use the predictions by the deep segmentation network, the UNet that we have trained on the first 5 VSIs. And we can make another results folder for the new dataset and pre-process and repeat and expand this active learning process to as many VSIs as you have in your dataset until you are happy with the performance of the neural network. Here we decrease the learning rate slightly for fine-tuning of the previously trained network. Another possibility is to run inference and visualization directly on VSIs using a third software called Pathology. You then use the export ONNX function in DeepMIB. After exporting the ONNX file, it will be saved in the DeepMIB folder. Next, one will have to go to no-code-seg GitHub repository and download a configuration file for this ONNX file. This must be saved under the same name as the ONNX file and saved in the same folder. This file specifies the input size of the patches the network is trained on, which is 512 by 512, as well as the magnification level, which here is set to 10x, which is downsample 4 from 40x. Also the mask threshold, tissue threshold, patch overlap, as well as the number of classes has to be set. The inference engine we set to OpenVINO, but you can also install TensorRT for a much faster GPU inference. You will now download Fast Pathology, in our case the Windows version. Fast Pathology has the ability to read ONNX files and run predictions on these, even though they are trained in DeepMIB. So after downloading and installing Fast Pathology, you will take the ONNX file and the corresponding configuration text file and move it to the C:user Fast Pathology data models folder. We then open Fast Pathology and choose create project. We create a new project folder. And then import the VSIs which you want to predict. So since you have placed this ONNX file in the models folder with the corresponding configuration file and specified the name, it appears as a button in Fast Pathology with a one-click prediction opportunity. So we go through all the VSIs and run predictions on each of them. Batch mode prediction is a work in progress and will be available soon. So after running predictions on all the VSIs, prediction is very fast. You will get resultant folders for each VSI with a corresponding TIFF file, which has the predictions coded into them. You can now open the no-code-seg repository on GitHub and copy the import pyramidal TIFF script and open QPath. So we find the VSIs, we delete the predictions which we imported from DeepMIB, just run it in batch, clear all objects. And then open the script editor, paste the import pyramidal TIFFs, and specify the folder where the BSI folders are placed. Set the downsample to 4, since that's what we have in this case. Test it on one slide, seems to work. The import is very fast, and then run it in batch for all the BSIs that you have predicted in fast pathology. This work is a collaboration between St. Olavs Hospital, the Norwegian University of Science and Technology, University of Helsinki, and SINTEF. All the scripts used in this study and the tutorial is available at GitHub, no-code-seg. The full data set of 251 column biopsies, whole slide images with 31,000 epithelial annotations, and the trained units will be made openly available at dataverse.no, no-code-seg. Thank you.